Hey everyone, and welcome to this explainer. Today we're going to take some pretty complex physical mechanics and transform them into a clear-cut story about cause, effect, and interaction. I mean, think about it. If you've ever watched a game of pool, witnessed a car crash, or even just stepped off a small boat onto a wooden dock, you have experienced the exact forces we're going to unpack today. We're going to look really closely at how objects carry motion, and exactly what happens when they transfer that motion to something else. So let's quickly run through our roadmap for today. We're going to start off with linear momentum, move right into impulse, cover the law of conservation, explore the different types of collisions, and then finish up with 2D glancing collisions. Let's dive right in.
Section 1. What is linear momentum? The protagonist of our physics story. Okay, so to truly understand motion, we first have to define our main character. You can basically think of linear momentum as the amount of motion a specific object has. It's the baseline we absolutely have to establish before any collisions or interactions can even happen. Mathematically speaking, linear momentum, which is usually represented by the lowercase letter p, is a vector quantity, and it's defined simply as the product of an object's mass and its velocity. Now, because momentum is mass multiplied by velocity, its direction is always going to be the exact same as the direction of the velocity itself. So if a giant heavy truck is moving east, its momentum is pointing east. It's really that straightforward, but it is incredibly powerful.
I want you to lock this unit into your memory right now. Kilograms, meters per second. That is the standard SI unit for linear momentum. You get this just by multiplying the mass in kilograms by the velocity in meters per second. Whenever we're tracking motion in any of these physics problems, this is the core unit you'll be anchoring your calculations to.
Moving on to Section 2. Impulse, changing the momentum, or as we like to call it, the external conflict.
Now we get to introduce the conflict. What happens when a force tries to change that momentum we just talked about? See, an object happily traveling along with its momentum won't just change course on its own. It requires an intervention, and that intervention is called impulse. Impulse is defined as the product of a force and the time over which that force is applied. Crucially, this is mathematically equal to the overall change in an object's momentum. Now, this single concept right here, it literally changed an entire industry. It completely revolutionized automotive safety. By designing cars with crumple zones, engineers intentionally increased the time of a crash by just a few tiny milliseconds, but increasing that time drastically reduces the lethal force transferred to the passengers inside. So impulse acts as this critical bridge between an object's current state and its future state. And just like momentum, impulse is a vector quantity, meaning it shares the exact same direction as the constant force being applied.
This graph is a brilliant way to illustrate how impulse works in the messy real world, where forces aren't always constant. When we plot an impulsive force against time, think of something like a tennis racket smacking a ball. The force spikes up and then drops back down. The shaded area directly underneath this curve represents the integral of force over time, which gives you your total impulse. It's just a really beautiful way to visualize the total change of momentum injected into a system during a split-second impact.
All right, Section 3. The law of conservation, balance in the universe.
This brings us to one of the most unbreakable, fundamental rules of classical mechanics, the law of conservation of momentum. This is where we see the universe acting as a perfect accountant, perfectly balancing the books on every single interaction. The crucial point here is that in an isolated system, which just means a system where no external forces like outside friction or air resistance are messing things up, the total initial momentum is exactly equal to the total final momentum. Regardless of the severity of a crash, the bouncing, or the sheer chaos of the interaction, the overall momentum before an event is identical to the momentum after. The motion isn't lost, it's simply redistributed among the objects involved.
Let's actually test this concept intuitively before we bring in any of the heavy math. Imagine a boy standing at one end of a completely stationary floating raft. He decides to walk to the opposite end of the raft, walking directly away from the shore. What happens to the raft itself? Think about it for a second. Does it stay still? Does it move away from the shore with him? Or does it move toward the shore?
Okay, let's break down the conservation logic here. The initial momentum of the buoyant raft system is zero, right? Because everything is stationary. But when the boy walks, he gains forward momentum. Now, because the total system must maintain that initial zero momentum, the raft has to slide backward toward the shore in the exact opposite direction. The positive momentum of the boy and the negative momentum of the raft perfectly cancel each other out, proving that the universe, without fail, always balances the books.
Section 4. Types of collisions. Elastic versus inelastic. So, Now that we know momentum is absolutely always conserved in an isolated system, let's explore what actually happens when two moving bodies physically smash into each other. While momentum is our constant survivor, we have to look at another factor to classify these collisions: kinetic energy. In an inelastic collision, momentum is conserved, but kinetic energy is fundamentally lost. It usually gets transformed into heat, sound, or physical deformation. And actually, tying back to how this science changed the auto industry, that physical deformation is exactly what automotive engineers are relying on to absorb kinetic energy and keep you alive in a crash. If the objects deform heavily or even stick together perfectly, it's inelastic. On the flip side, an elastic collision is a perfect, idealized scenario where both momentum and kinetic energy are fully conserved.
A Newton's cradle, which you've probably seen on someone's desk, is the perfect visual representation of an almost completely elastic collision in action. One sphere strikes the pack, and precisely one sphere kicks out the other side. It transfers both motion and energy flawlessly from one end to the next, with virtually zero kinetic energy lost to deformation.
Let's do another quick quiz, but this time with a highly destructive, perfectly inelastic collision. Imagine a small car and a massive truck traveling at the exact same speed. They collide head-on, they crumple, and they stick together. Which vehicle undergoes the larger change in the magnitude of its momentum? Is it the massive truck, the smaller car, or is it the same?
Now, it feels completely counterintuitive given the massive size difference, but the correct answer is that the change in the magnitude of momentum is exactly the same for both vehicles. Remember the law of conservation we just talked about? Since the total momentum of the isolated system must be conserved, any momentum the truck loses must be exactly gained by the car. The magnitude of change for the car perfectly mirrors the magnitude of change for the truck. Now sure, the physical effects on the passengers will be vastly different due to mass and acceleration, but the raw momentum exchange, it's a perfect equal swap.
Let's head into Section 5, 2D glancing collisions, taking physics off the straight line. Up until now, we've really only looked at head-on, one-dimensional crashes. But let's be real, the real world is messy. What happens when objects don't hit dead center, but they strike at an angle? When mass 1 comes in horizontally along the x-axis and strikes mass 2, both objects suddenly deflect off at totally different angles. They scatter into 2 dimensions. This means we can no longer just do simple addition and subtraction. We now have to track their conserved momentum both horizontally on the x-axis and vertically on the y-axis.
Because momentum is a vector, it can be mathematically resolved into these different axes. We essentially look at the angle of deflection for both objects and use a little bit of trigonometry. We use cosine to find the momentum components traveling along the x-axis and sine to find the components traveling along the y-axis. By splitting the problem in half like this, we can keep our calculations perfectly organized and ensure that momentum is conserved in both directions entirely independently.
And by breaking the problem down into these specific 3 steps, you can solve some wildly complex 2D collisions without getting overwhelmed by a giant wall of numbers. Step 1, always identify your initial masses and velocities before the crash. Step 2, resolve your final velocities into those x and y vector components using the sine and cosine angles we just talked about. And finally, step 3, apply the law of conservation to both the x-axis and the y-axis independently to solve for your unknown variables.
For example, we can apply these principles of conservation and momentum to a really cool scenario like this one from our source material. Here, a tiny 3.50-gram bullet is fired horizontally. It passes entirely through a 1.20 kilogram block and then embeds itself permanently into a 1.80 kilogram block sitting on a frictionless table. By tracking the mass and the final velocities of those 2 blocks, you can play detective and work entirely backward to calculate the initial blistering speed of that bullet.
Or we can use our 2D glancing collision steps on this classic setup. An incoming billiard ball traveling at 17 meters per second strikes an identical stationary ball. They scatter, one deviating by 45 degrees, the other by 30 degrees. By setting up our x-component equation with cosines and our y-component equation with sines, we can perfectly predict the future speeds of both of these balls as they scatter across the table.
As we wrap up this explainer, I want you to step back and look at the much bigger picture. We've talked about pool balls, rafts on the water, and how impulse reshaped the entire automotive industry with car crashes. But these laws of impulse, vectors, and unyielding conservation, they don't stop at the edge of Earth. I want to leave you with this final thought. If the universe perfectly tallies every single exchange of momentum in every collision,
How do these exact same equations govern the epic cosmic collisions that built our galaxy, shaped our planets, and continue to dictate the dance of the stars? The math is exactly the same. It's literally just the scale that changes. Keep exploring, keep questioning, and I'll see you in the next one.